the energy unit. We're going to introduce this term called mechanical energy, okay? Now, what specifically does mechanical energy mean? Mechanical energy is, in the context of this course, energy that is going to be useful to us, okay? And the precise definition of useful is going to be covered just a little later in the video, but first let's try to understand it conceptually, okay? What do we mean when we say energy is useful? Like, let's say I have a rock, and I'm holding a rock up here in my hand, high up above the ground. And let's say I have a turbine that's connected to a generator. If I drop the rock, if I let go of the rock is going to be able to turn the turbine and generate electricity, okay? Therefore, the gravitational potential energy of the rock is useful to me. I was able to use that energy to generate electricity. I was able to convert it to a useful form of energy, okay? Another example of that would be, let's say, the energy stored in a spring. If I were to release the energy stored in the spring, if I were to let go of the energy stored in the spring, I could use that energy to turn a turbine. You know, if I have one paddle of the turbine and I release the spring is going to be able to push on the turbine and generate electricity. It can become a useful form of energy. So that's two types of energy we've discussed so far: spring potential energy and gravitational potential energy. Now let's discuss some examples of energy that is not useful to us. For example, small amounts of heat energy, not useful to us. How is heat energy going to be generated? It's going to be generated, like, let's say when you rub your hands together in a cold environment to try and warm up your hands. That's going to generate a small amount of heat. But I can't do anything with that heat energy. That energy isn't useful to me. I can't generate electricity with it. I can't power my home with it. It's not something I can use. Another example of non-useful energy is going to be sound. If I slam my whiteboard, it's going to release a bunch of sound waves, and sound is a type of energy. That energy cannot be useful to me. I can't use it to do anything meaningful. Mechanical energy is useful energy that is available to us. So based on the examples I just provided to you, gravitational potential energy and spring potential energy are examples of mechanical energy, okay? Very integral to our understanding of this unit is going to be the law of conservation of energy, okay? And we are largely going to be exploring the law of conservation of energy mathematically. When we say mathematically, we mean that if we calculate the sum total of all of the energy we have in a system being like a defined area within which we are considering the participants or objects interacting inside that bound space, if we consider the total amount of energy in that area, the change in that energy must always be zero if we are dealing with a closed system. What do I mean when I say closed system? Closed system is defined that there are no external forces acting on the system, and there is no energy entering or leaving the system. Our solar system, for example, would be an example of a closed system. However, in the law of conservation of energy, we just say that the total energy can't change. However, individual pieces of energy can change forms as long as the total amount of energy is held constant. In my examples, I showed you how gravitational potential energy with the rock I held up in my hand, when it started falling and it hit the turbine, it turned the turbine. So the gravitational potential energy we started with up here was converted to electrical energy as the turbine turned the generator, okay? So even though I lost gravitational potential energy when I released the rock, I gained electrical energy. Okay, so the total amount of energy in the system remained constant. All right. Now, when the rock collided with the turbine, that released a sound. So not 100% of my gravitational potential energy was converted to electrical energy. Most of it was converted to electrical energy, and a small part of the energy was lost in the form of sound waves. So that, therefore, leads me on our discussion of the types of energy. So first of all, the most common, the most fundamental type of energy is kinetic energy. As the name might imply, kinetic energy involves motion, okay? If you notice, whenever you try and throw a baseball, you personally, your human being must exert energy onto the ball in order to accelerate it, in order to give the ball a velocity, okay? The chemical energy stored in your muscles must be used up in order to impart velocity onto the ball. So we have equations that allow us to analyze exactly how much energy the ball possesses. Kinetic energy, as from your reference table, is equal to 1/2 mv squared, such that m is with reference to the mass of your object, in this case the mass of your ball, and velocity squared is the velocity of your object, okay? So let's also discuss the unit of energy. The unit of energy is the joule. Let's try and figure out the joule as it is represented in fundamental units, okay? We can use this equation to try and figure that out. We know that the joule is equal to a constant times the unit of kilograms per mass times the unit of meters per second squared, okay? Therefore, the joule is equal to a kilogram meter squared per second squared. And we can see why that is true from our equations. So if you'll notice here that kinetic energy is proportional to velocity squared, a lot more energy is required to accelerate something from 10 meters per second to 12 meters per second than the amount of energy required to accelerate something from 2 to 4 meters per second. So let's understand where kinetic energy can come into play. Let's return to my rock example, where I held a rock above the ground. But the moment I release that rock, the moment I'm no longer holding onto the rock, gravity is allowed to accelerate that rock, okay? So the force of gravity acting on the rock is speeding up the rock. Therefore, the rock is gaining kinetic energy as it is falling, okay? And the force of gravity acting on that rock means that the gravitational potential energy that we initially started with up here is being converted to kinetic energy of the rock. And then when the rock collides with the turbine, the kinetic energy of the rock is what is pushing the turbine, okay? And since the turbine was stationary and now it's moving, the turbine gains kinetic energy from the kinetic energy of the rock. And the turbine will spin, and the turbine will begin to slow down as the kinetic energy of the turbine is transformed into the electrical energy by the generator, okay? So in a fairly simple system, as I've described to you, you see energy changes form many, many times, okay? Now, that leads us to our discussion of work, okay? You will recall previously that I discussed what is useful energy. Useful energy is defined as energy that is capable of doing work, okay? Now, let's discuss what work is, okay? Work is something that can either be done onto a system or work can be done by a system. If we want to translate that into English, we say if work is done on a system, you are imparting energy, you are adding energy to the system, okay? If work is done by the system is losing energy, total energy, okay? The formula for work, since we are a calculus class, is given in the integral form, such that the work is the integral from point A to point B of force as a function of x dx, with the force and displacement being vectors, okay? Your equation sheet gives it with dr, but what's important in this integral is our dot product right here in the center, okay? The importance of the dot product is that there is another term that it signifies, okay? So we can rewrite this integral, if we don't want to deal with the messy dot product, as the work done is equal to our definite integral from a to b of the magnitude of the force function multiplied by the cosine of theta dx. Okay, so what does this equation mean? It means that work is done when a force is acting through a distance, okay? And since this is the integral form, we are evaluating a changing force multiplied by its position or displacement differential, okay? So an example of that would be the rock example I just mentioned. If I'm holding a rock up here above the floor, and if I release that rock from rest, the gravitational force is now acting on the rock, okay? The gravitational force is acting on the rock, but during the point in time where I'm holding onto the rock isn't moving, okay? So that is an integral component to our work equation. There must be a dx, there must be a change in position, there must be a displacement in order for work to be done. So no work is done if the rock doesn't move. The moment I release the rock starts moving, okay? Let's say I evaluate the work done between point A, which is its initial point, and point B, once it reaches point B, okay? So this movement, this displacement, gives me a displacement vector, okay? And that's represented by this arrow, okay? The gravitational force vector can also be represented by this arrow, okay? Such that cosine theta is the cosine of the angle theta between our two vectors, because force is a vector and displacement is a vector, okay? So you'll notice in this particular example that our displacement, the distance our rock has traveled, and the force vector are acting in the same direction. So that means the angle theta between them is 0, okay? So cosine theta, when theta is 0, simplifies to 1. But the presence of that term is significant because it states that the work done by an object decreases as the angle between the displacement and force vectors increases, okay? So for example, maybe instead of letting it go, I pushed the rock to the right. So that would stipulate that the rock would have a displacement vector to the right as such, okay? And I would have a position A right here and a position B right here. That's my displacement vector, but my force vector, the force of gravity, is still pointing downward. Therefore, in this case, I do have a non-zero angle theta between my force vector and my displacement vector. So that will decrease the overall work done by the force, okay? We can also understand why this representation makes sense, because it's a multiplication of force times displacement. Force is in units of newtons, which are kilogram meters per second squared. And if we multiply that by position, which is in units of meters, we get the joule, which is kilogram meters squared per second squared, as stated previously, okay? What can we interpret the work as meaning, okay? What does the work actually mean in this particular scenario? So let's stick with this example. Recall that the force of gravity near Earth's surface is just mg, okay? Our gravitational constant g is a constant, so it's not changing, and the mass of our ball is not changing. Therefore, the force of gravity, F sub g, is a constant. So we can rewrite this integral as being the work done from A to B of F sub g cosine theta dx, where given that our cosine theta is not changing and our force of gravity is not changing, both of these can be taken out of our integral. Therefore, the work done is equal to the force of gravity times cosine theta times the integral from A to B of dx, which is simply just the force of gravity times cosine theta times b minus a. Okay? The force of gravity is acting on the ball, okay? But only a portion of the force of gravity is acting on the ball, as stipulated by this theta, okay? Therefore, the ball is given an acceleration by the force of gravity, and since it has gained an acceleration by the force of gravity, the ball has gained kinetic energy, okay? Therefore, we can say that work has been done on the system, okay? An easy way to recognize this is if your force vector and your displacement vector are operating in approximately the same direction, then work is being done on the system. Okay, what do I mean by approximately? I mean if I have a force vector and a displacement vector, we define those as being in the same direction until they are exactly perpendicular. Okay? And we define them as being in the opposite direction if they are at any angle theta between 180 degrees and 90 degrees. Okay? So work is being done on the system when our angle theta here is 89 degrees. And work is being done by the system when our angle theta is 91 degrees. Okay? So what happens at particularly 90 degrees? Well, cosine of 90 degrees is 0. So if we plug that into our integral, we get the integral of 0, which is 0. So therefore, if we are calculating the amount of kinetic energy or energy as a whole gained by the rock as the force of gravity is acting on it, work can otherwise be defined as change in energy. That is what work is. It is the change in energy of a system, or it is the change in the form of energy, rather. Okay? Work specifies how much gravitational potential energy has been converted. Work specifies where that gravitational potential energy has gone. Okay? So if we do our work integral, if we calculate the force of gravity multiplied by our cosine theta times b minus a, that will give us the amount of energy lost by gravitational potential energy, how much gravitational potential energy was lost, and therefore, since we know how much was lost, we know how much was gained elsewhere. And we need to ask ourselves, what form of energy is being gained in this scenario? The kinetic energy of the rock. So we can say that the kinetic energy of the rock in this example is equal to our work integral of the force of gravity with respect to the cosine of the angle theta between them, dx. Okay? And when we evaluate that integral, we can set that equal to the formula for kinetic energy, which is 1/2 mv squared. Okay? So in this scenario, given the mass of the ball and the angle theta between the displacement and force vectors, given only those two quantities, you would be able to calculate the velocity of the ball. Of course, that velocity of the ball would only be accurate at the position you are describing, at the position you're analyzing, okay? You have an initial position A, and you have a final position B at which you are analyzing the energy of the ball, at which you're analyzing the velocity of the ball. From there, let's start our discussion of the different types of potential energy denoted by the letter U. Okay, don't ask me why. But first of all, let's try and mathematically explain the gravitational potential energy that I've been describing to you thus far. Now, even though the equations for potential energy are given to you on your reference table, it would be useful to us to understand how to derive them. And understanding how to derive them will give us a better understanding of why they work the way they do. Okay? For example, let's talk about gravitational potential energy, U sub g. Okay? First of all, we know that the force of gravity, F sub g, is equal to the mass of an object times the gravitational constant g near the surface of Earth. If I was trying to take this marker and I was trying to raise it upward, if I were trying to give gravitational potential energy to the marker, I would need to apply a force that opposes the gravitational force. Okay? So, if I were to look at this in the context of my work integral, I would take my work integral, the work done on the marker, as I'm raising it upward, as I'm giving it gravitational potential energy, would be its initial position A to its final position B. Of course, we're dealing with position in the y direction because I'm raising the pen upward, would be equal to the force of gravity acting on the marker, dotted with the displacement differential vector. So in this case, the force of gravity would be acting downward, but the marker would be moving upward. Therefore, if I rewrite the dot product with cosine theta, my cosine of theta being 180 degrees, because they are exactly parallel and acting in opposite directions. So cosine of 180 is -1. So in fact, this would be the integral from A to B of my gravitational force multiplied by -1 dx. Okay? So let's try and evaluate that integral. First of all, gravitational force is a constant in this example. So we can take that out of our integral. So therefore, the work being done by the marker is equal to the negative force of gravity, or rather I could rewrite that as mg, multiplied by the integral from A to B dx. Okay? Therefore, that equals negative mg times b minus a. Okay? And since we're dealing in the y space, we're dealing in the vertical direction, b minus a is simply our change in y, or our change in height. So this, of course, represents the work done by the marker, okay? Because the marker is moving against the gravitational force, so work is being done by the marker, okay? Like I said before, when our work is negative, work is being done by the system. When our work is positive, our work is being done on the system, okay? The work done by the system is equal to the negative work done on the system, okay? So, if our work done by the system is mg delta h, then our work done on the system, the increase in our gravitational potential energy through this motion, is equal to the negative of this value, mg delta h. Therefore, using the work integral, we have derived the equation for gravitational potential energy near Earth's surface, which is given to you on your reference table, right at the bottom left-hand corner, okay? Your change in gravitational potential energy is equal to your mass times the gravitational constant g times your change in height, okay? Which makes sense. If I raise the marker up, I gain gravitational potential energy. If I allow it to fall back down, it loses gravitational potential energy. Okay. Another form of potential energy that we are to be made aware of is spring potential energy, okay? Because when you compress a spring and you keep it compressed, the spring stores energy. The spring stores the ability to accelerate something else when you remove the barrier on it, okay? So first, let's derive this thing. We know that the force on a spring is equal to, by our reference table, k delta x, or excuse me, negative k delta x. So for the purposes of this derivation, we're going to assume that our initial position is 0. Therefore, this equation simplifies to negative kx. So I want to do the work integral. I want to find how much work is done on the system as I oppose the spring force and I try to compress it, okay? So my work integral from initial position 0 to final position x is equal to the spring force dotted with the displacement vector differential, okay? Now, in the case of the spring, if I'm compressing a spring, my force of compressing it is acting exactly opposite to the force that the spring is applying to me. So, therefore, we can simplify the dot product and simply write this as the negative force, because there's an angle of 180 degrees between displacement and force, which is cosine of 180 is -1. Therefore, it will be rewritten as the integral from 0 to x as our spring force, the negative of which is a positive kx dx. K being our spring constant, therefore it will be brought outside the integral. And we're left with the integral from 0 to x of x dx, which is x squared over 2 evaluated from 0 to x, which is just x squared over 2. Okay? We don't forget our spring constant k. Let's bring that back in. And therefore, we have derived the equation for potential energy stored in a spring equals 1/2 kx squared. The potential energy stored in a spring increases exponentially as you compress the spring farther. Okay? Why does the energy increase exponentially? Because the force you apply to that spring increases the further you compress it. Therefore, by our work integral, the more force being applied, the more energy or the more work is being done. So given that understanding of potential energy, since the potential energy in a system is always trying to release itself, the potential energy doesn't like to stay potential, it likes to be released, like in the case of gravitational potential energy. If I leave the system be, if I release my marker from rest, the gravitational force will release its gravitational potential energy and try and convert it to kinetic energy. Okay? Therefore, we can interpret this work integral in terms of the derivative. Okay? So let me differentiate that. The derivative of work. So we say the derivative of work, which is the equivalent of energy with respect to position, because this is a derivative with respect to position, equals force. Okay? Now let's specify what kind of energy. Okay? The work integral is meant to identify the work done on a system. Okay? So the change in kinetic energy of the system with respect to x is equal to the force applied on the system. Or we could interpret it in terms of the work done by the system, or the negative derivative of potential energy with respect to x equals the force applied to the system. Okay? So let's try and interpret that in context. Return to gravitational potential energy. At the top, I have gravitational potential energy, and as my marker starts falling, my potential energy is decreasing. Okay? So if my potential energy is decreasing, that means that the rate of change of my potential energy is negative. Okay? So since the rate of change of my potential energy is negative, a negative times a negative makes a positive, and that therefore gives me the gravitational force acting on the marker. Okay? As the marker begins to fall, its velocity is increasing, therefore its kinetic energy is increasing. So since the rate of change of kinetic energy is positive, we are given a positive force, positive gravitational force acting on the marker by this derivative. Okay, so let's use the work integral one more time to derive the equation for gravitational potential energy far from Earth's surface. Okay, we're going to return to our reference table, and we're going to pull the equation for gravitational force, the fundamental gravitational force, which states that Fg equals big G m1 m2 over r squared. If we are calculating potential energy, we're going to try and gain potential energy. Okay, so we're going to try and act against the force of gravity. Okay, if I want to calculate how much gravitational potential energy the moon has, I'm going to try and calculate how much energy is required to move the moon from the center of Earth out to where it is. So that is going to be the displacement through which I calculate. Okay, my work done is going to be from the 0 radius, from the center of the Earth, all the way out to the radius at which the moon is orbiting. Okay, multiplied by my gravitational force, big G m1 m2 over r squared. In this case, we're going to do dr. Okay, remember how I said that r, x, and d operate interchangeably. They're all variables of distance or displacement. Okay, Again, don't forget to evaluate your dot product. In this case, we're going to assume that the path taken from the center of the Earth to where the moon is now is a completely straight path, and that the gravitational force is acting exactly opposite to our displacement vector. If this is the Earth and this is where the moon is supposed to be, the Earth is trying to pull the moon this way, and we are trying to push the moon that way. So our cosine theta evaluates to a negative. Therefore, the work integral can be rewritten as such: negative g m1 m2 over r squared. We know that g is a constant. The masses of our two planets will not be changing in this scenario. Therefore, we are going to be pulling those outside of the integral and rewriting the integral as such: 1 over r squared dr. Therefore, the integral in this case is going to be negative 1 over r, evaluated from 0 to r, our final distance of the moon, which is just going to be our negative 1 over r. So we are therefore left with gravitational potential energy equals g m1 m2 over r. Okay? Now, for some weird physics convention that I personally don't quite understand, we are going to keep the negative because the scientists upstairs, the people who govern physics, say that we want gravitational potential energy to operate on the negative scale, such that when you are an infinite distance away from an object, you have 0 gravitational potential energy, and when you're closest, you have negative infinity gravitational potential energy. Okay? Such that me standing on Earth right here, my absolute gravitational potential energy would be a very, very negative number. Okay? Where if this negative was not here, we would say that if you're an infinite distance away from an object, you have an infinite amount of potential energy. Okay? But if you need some help clearing up why this is, be sure to join my Discord and ask me personally, because it's a bit too long of an explanation for me to do right here in the video. This is not a concept that is integral to your performance on the exam. It's just important that you understand where the numbers come from. And the presence of the negative is sort of an afterthought. As long as you have the equation on your reference sheet, you're going to be fine. Okay? Now, moving on from there, we have the discussion of conservative forces. Okay? It's not political, I promise. So, what is a conservative force? A conservative force is a force that conserves usable energy. The force of gravity is a conservative force. All right? If, let's say, I do work on the marker and I raise it up against the force of gravity will act on the marker again and will impart kinetic energy, sending it back down. Okay? So when you are dealing with a conservative force, when you are dealing with the work done by a conservative force, the resultant energy from the conservative force acting through a distance can also be used to do work. Okay? So for example, I have a marker up here with gravitational potential energy, and I have a spring down here. Pretend there's a spring in my hand. If I were to release this marker, gravitational force would do work on the marker, and it would impart kinetic energy onto the marker. Okay? That is basically the definition of a conservative force. A conservative force can convert energy into a usable form. If a conservative force is acting on an object, the conservative force imparts kinetic energy. If the object is acting against a conservative force, then the object is converting energy to potential energy. Okay? So, for example, this marker at the bottom of its descent will act against the force of the spring. Okay? And since the marker is acting against the conservative force of the spring, the energy of the marker is being converted to potential energy, specifically the potential energy of the spring. Okay? And that potential energy of the spring, since the spring force is a conservative force, is going to re-impart that energy back to kinetic energy of the marker, okay? So conservative forces do work, and in their doing work, they preserve the total amount of usable energy. They preserve the total amount of mechanical energy. That is in contrast to a non-conservative force. This primary example of a non-conservative force is the frictional force. If I have a table and I'm sliding my marker across the table, let's pretend that the marker isn't rolling. If I slide my marker across the table, the marker will endure the force of friction, and the force of friction will do work on the marker, okay? Force of friction dotted with dx. In this case, the force of friction is operating against the velocity of the marker, and the velocity of the marker is continuing to the right. Therefore, negative work is being done. Therefore, energy is taken away from the marker. Kinetic energy is taken away from the marker, okay? So the frictional force takes away the kinetic energy of the marker and slows it down, okay? Once the marker has been completely slowed down, all of its kinetic energy is gone. Where did all that kinetic energy go? The frictional force converts energy into small amounts of heat. That's why we described heat as not a mechanical form of energy, okay? Heat is not a useful form of energy. Heat is not included in our calculations involving mechanical energy, because small amounts of heat cannot be used to do work, okay? Small amount of heat can't accelerate my marker. Small amount of heat can't give me gravitational potential energy, okay? That is a non-conservative force, okay? So therefore, total mechanical energy in a system must always decrease if there are non-conservative forces present. In a system where there are only conservative forces, mechanical energy will always be conserved, okay? Do not get conservation of mechanical energy confused with conservation of total energy, because even though we have lost useful energy, we have not lost energy. Heat is still energy. We have still conserved the total amount of energy in the system, but we have lost usable energy. We have lost mechanical energy. Okay? So moving on from there, we have the very simple topic to wrap up the unit, and that is the topic of power. Okay? Power and energy are often confused. Power is defined by a very simple equation. Power is represented by the capital P, and it is the derivative of energy with respect to time, or the derivative of work with respect to time. Energy and work are often used interchangeably. Okay? So if work is being done on a system, that means the energy of the system is changing. What does power therefore mean? Power is the rate of change of energy with respect to time, so it's basically saying how much energy is being given to the system per unit time, or how much energy is the system giving me with respect to time, okay? For example, an engine is not rated in its supply of energy, it's rated in its supply of power, specifically the American non-metric stupid unit of horsepower. Horsepower is a unit of power. Horsepower says how much kinetic energy can this engine supply to your car every second. The total amount of energy that the car can supply to you is not based on the engine, it's based on the amount of gas you can carry. Derivative of energy with respect to time can be illustrated with an example like this, okay? If I am at a practice, if I'm doing a workout, and I need to run up a bunch of stairs as part of the workout, let's say that the top of the stairs is 100 meters high, and I am starting at 0 meters. My gravitational potential energy, my change in gravitational potential energy, is going to be my mass, which let's say is 60 kilograms, 60 kg, times g, which is 10, times my change in height, which is 100. Therefore, my change in gravitational potential energy should be 60,000. So that's the change in gravitational potential energy between these 2 points, okay? However, if I sprint up the stairs versus if I walk up the stairs and I take 10 minutes to get there, the total amount of gravitational potential energy doesn't change, okay? Therefore, the total amount of energy I need to expend in order to get from top to bottom doesn't change. Speed at which I rise the stairs is not affected, or does not affect, the total energy or the total work done on the system. Okay? Power, the derivative of energy with respect to time, the rate of change of energy in time, is the thing that is varied by how long it takes me to do that energy. Okay? So if it takes me 100 seconds to rise up the 100-meter staircase, then the power being supplied is going to be 60,000 divided by 100 if I expend a constant amount of energy, which would be 600 joules per second, or the unit of energy the unit of power 600 watts. The correct unit of power, not horsepower. Power expended in that scenario would be 600 watts. Therefore, the higher wattage, the higher power rating of your engine, the more energy it can supply every second. Okay, so the higher horsepower that your engine has, the faster your car is able to go. The more energy it is able to supply to your car per second, which is useful in overcoming the force of friction between your car and the road and your car's transmission with the rest of the components in the car. Okay, that's energy, guys. Thanks for watching.